Hello, 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 hello.
So at this point, we're just taking a few more minutes to, let you keep working with your projects, test them out on the boards, debug. So for the next few minutes, I'm just going to walk around, help out, see how you're doing. And then after that, we'll pick up with more exercises. I guess I should comment too for the folks who are virtual. Of course, you don't have the physical boards. Uh, Not a problem. Everything that we're doing, you can do virtually. You'll miss out on the physical. Working. So it looks to me like most of you have been able to program your devices and debug the behavior of your circuit. If you didn't get through all of that, it's not a big deal. Nothing that we're doing now with the walk-we flows, none of the future materials dependent on that. It's just a chance to get comfortable with the FPGA boards and play around with circuits in more of a drag-drop style to, work at the logic gate level. On, we're going to shift gears to the Makerchip platform, where you're doing your design hardware description. So to start us out, I'm just going to walk through the platform myself. You can open up just makerchip.com and then launch the IDE. So I'm just going to demo the platform, show you how to navigate around, and then we'll have a short lab exercise for you to navigate around the platform. So let's see. This is basically what you would expect of a circuit design IDE for the most part. You've got your editor window where you can enter your code. I'm going to open up a design that's a little bit more interesting. So I'll open up this long division circuit. So when I loaded that, it compiled automatically. You can compile up here under the editor's E menu. When you compile, you get a logic diagram generated from your code. You get waveforms. You can split windows, drop the waves down here. This Viz tab we'll get back to. Get to that later. So anybody here not used a waveform viewer before? Okay, so this is what you would expect of most waveform viewers, except that it has some awareness of transaction level Verilog. But here you've got the design hierarchy that you can expand. It's a fairly primitive waveform viewer. It doesn't have some things that most waveform viewers do. Most waveform viewers, for example, let you sort the signals, grab a signal and move it somewhere else so you can put related signals together. This waveform viewer does not have that capability yet. It is going to organize your signals based on the hierarchy of your model. What it does have that's somewhat unique from other platforms is it's integrated with the IDE. So as you're debugging your circuit, you may be debugging by looking at the waveforms. Maybe, let's say, this assertion here looks wrong to us, this last iter signal. You can click on that. It's going to highlight in the logic diagram so you can help get yourself context of what the circuit is doing. And it's also going to highlight in this nav TLV tab, which is also representing your source code. This tab is kind of your source code as seen by the tools. And it's also called nav TLV because it's your TLV code that's navigable. It's meant for debug, right? You can find your way around by highlighting signals and such. So if I scroll down, I see that signal that I highlighted from the waveform is highlighted here, so I can correct the logic function, whatever the issue might be. If I click on this line number, 86, it'll take me back to line 86 in the source code to fix the error. What else about the platform? So if I open up the help menu, you'll see some information about keyboard shortcuts and so on. But mainly I opened that up to show the diagram to illustrate what's happening behind the scenes. You're editing your code in the editor, you click compile, your code gets sent to the cloud, to the Makerchip server to run through processing of your transaction level Verilog code, which is done by Sandpiper, a Redwood EDA tool. So this is taking your TL-Verilog code and spitting out Verilog or system Verilog. Before Sandpiper, there's a macro preprocessor that's run. Mainly in this course, we're not really using macro preprocessing to do any code generation. So mainly Sandpiper is what matters, which is TLV to system Verilog. When you get, the system Verilog is then passed to Verilator, which is an open source simulator. So it's going to compile your Verilog code, create a simulator model out of it. That is a C++ based simulator, so that simulator gets compiled and executes your simulation, produces trace data, which you're viewing in the waveform. Okay, and all of these tools produce log output that gets collected up, represented back to you in this log tab. The log tab has the blue section here, which is from the TL-Verilog syntax processing. This is from Sandpiper. And the black section is from Verilator doing the Verilog compilation and simulation. Let's see what else. Under the project menu, if you're running, so some web browsers permit access to your local file system with permission. Some web browsers don't. If you're using Chrome or Edge, you shouldn't have any issue. They allow you access to your local files. Firefox does not. So if you have the option, you probably want to run Chrome or Edge versus Firefox. So you can save your file. Once you save it, I'll just do this as a demonstration. So once you save it, you'll see the green icon in the upper right here saying it's saved. If I go back to the editor and make changes to my code, this turns blue and it's auto-saving. So it auto-saves, turns green again. So once you've saved your file, you're linked to it. It's auto-saving to that file. Yeah, I think that's basically all we're going to use in terms of the project menu. Learn menu, it's got tutorials, examples, courses, specs. That's about it. So I think that's everything you need. So the quick lab here is to basically just follow these steps and to get you comfortable with the UI. Once your screen looks basically like this, you've completed those steps, and if you are able to produce this screen, you're able to interact with the IDE. So I'll give you 3 minutes just to walk through those steps. So out equals in is our inverter. And we compiled that either from the E menu or keyboard shortcut Control Enter. And we can see in the waveform that we do in fact have an inverter where the output is the inverse of our input. Questions? Yeah. Yeah, and you guys left it up to the professor to ask the question. You guys are too shy. So in the MakerChip platform, if you have dangling inputs, which I do here, those are warnings. My circuit is not valid with a dangling input. And I do see the warning here that my input is dangling. It's used but never assigned. And that my output signal is produced. It's assigned, but it's never used. Okay. Your model is going to compile anyway, and the MakerChip platform will just go ahead and create random stimulus for you on this dangling inputs. So this is probably one of the features that people really like about MakerChip. It's very simple. I don't know why other platforms are not kind enough to do this for you. Obviously, as your design gets bigger, you're going to want more intelligence in your test bench, and you're going to want to, control how the stimulus is provided. But I find you can, create a reasonable circuit in most cases just with random input. So this allows you to just jump in and code some logic real quickly, as we have done with our logic gate. Of course, we can do other logic expressions, right? So maybe in 1, 2. Okay, and we can see that the output is only asserted when both inputs are asserted. Arithmetic expressions. So I can give a bit range on this output signal. So let's operate on a byte, say. And we'll operate on 2 values. I'll make these 7-bit values, I guess. 2. Okay, so 7 plus 0 is 0. How'd that work? In 1 plus in 2. This time 7 plus 0 is 7. Through the numbers. The values in the waveform are in hexadecimal. You can hover over them and see binary and decimal. And of course, you can use parentheses to group expressions. Yeah. Yeah, so signals, these are called pipe signals. The reason for that will become apparent later. But yeah, we reference the pipe signals with $signs. 3. Okay. So just for reference, these are Verilog expressions, right? Boolean math has evolved through various disciplines in different ways and adopted different syntax. So depending who you are and what hat you wear, you may have seen these different syntaxes for Boolean logic. In Verilog, expressions are these. Most of the operators have a Boolean operator and a vector operator, right? So for example, the exclamation mark is a Boolean operator. That means A should be a Boolean value, 0 or 1. This tilde is a vector operator, meaning A can be a vector of, however many bits. This operator, the tilde inversion operator, is going to operate on every bit independently, so it's going to invert every bit. And similar for AND, you've got a Boolean form and a vector form. It's perfectly fine to use the vector form everywhere. That was our convention at Intel. It seems a bit excessive to have both forms to me, but sometimes it's nice just to sort of distinguish this is Boolean operation versus operating on vectors. So anyway, with this in reference, open up Makerchip and just play around with these operators, right? You can try arithmetic operators as well. Right. So this next lab is to use those logic expressions, and, multiple logic expressions, hooking up their inputs and outputs to create this circuit that we've looked at already, the full adder. So you can use this name for this intermediate node. This logic expression right here that I've circled, let's go ahead and create that all as a single expression. So use parentheses to group sub-expressions. And these two you can code as independent expressions. So again, 3 spaces of indentation, spaces around the equals. Just a quick note on why are we so rigid, right? So one reason is that it's layered, and we have to be able to distinguish Verilog syntax from TL-Verilog syntax. But more importantly, it's very rare anymore in the industry that you're writing code from scratch, right? We tend as programmers to like the personal freedom of formatting our code how we like it formatted. What's actually more important in industry, where you spend most of your life working with other people's code, is that you can look at their code and understand it. And so because of that, TL-Verilog has taken a very rigid stance on formatting space-sensitive language. The number of spaces of indentation matters. Tabs are not standardized spaces they represent, so forget tabs, no tabs in TL-Verilog. This way, your Verilog looks like your neighbor's Verilog, and when you're working together, you're speaking the same language. So it's really freedom of expression versus freedom of understanding. So we lean on the side of uniformity with TL-Verilog. Okay, so go ahead and try to code that up. All right, so I'll walk through this. So if you had any difficulty with it, you can watch me walk it through. So these are all Boolean signals, so I don't need any vector ranges. Uh, for B equals. So I'm going to start with this expression to drive this node. So that's an XOR gate, so that's going to be the AA input, XOR B input, and then to the next XOR gate, which is producing SS, it's going to be this, or CC in. For CC out, the out is 4 of 2 sub-expressions. First is the AND of C in and A XOR B. Okay, so that should be everything in my circuit. And I'm not going to figure out, bit level what's happening here, but that should be it. In trouble? I saw a lot of people trying to use assign statements and always blocks and declaring their signals. Don't need that in TL-Verilog. Is there a question? Yeah. So here I'm just taking advantage of microchips' ability to drive random stimulus, right? So we just have this circuit floating in space. So these inputs are just left dangling. Makerchip is just giving us random values. Likewise, the outputs are just left dangling. So yes, to create a complete simulation, we would define a test bench that's going to drive the stimulus. We would be checking on the outputs, so on. But I'm just taking the shortcut here and just dropping down that logic. Okay, everybody good? That was all Boolean, so let's try some vectors. Yeah, so I guess you can look through this. It's just more playing around with the syntax, playing around with the vector syntax. So expressions like this, right? This is using the bitwise AND. So it's going to do an AND on every bit. So you can play around with that, see the hexadecimal values and the waveforms, convince yourself that it's actually doing a bitwise AND. So again, I'll just give minutes to play around. Let me comment on a few things about debugging. Um, I have a bad habit of writing code that works and not giving students a chance to see what you do when it doesn't work, which is most of the time, right? So if I code a syntax error here, for example. So anytime you see these red X's on, the red X's on viz here, in that case, just viz, that's an indication that compilation failed. Every time you compile, you should look at your logs. There's no sense spending time trying to debug behavior that's wrong if you've got a log message telling you exactly what's wrong. So keep the log window handy. It's probably worth splitting the window as long as you've got screen real estate and just keeping the log at the bottom. So in this case, let's see. So here I have a bunch of warnings. These are all the dangling inputs and outputs. Those I expect. And everything gets through Sandpiper with those warnings and continues on to Verilator. Verilator is reporting a syntax error. That's because I deleted the semicolon, so this statement led into the statement. If I instead have an error in the TL-Verilog syntax, which that should be an error. Somehow it didn't care. I was okay with that too. Anyway, if I have a syntax with the TL-Verilog expressions, it won't be able to compile, it won't be able to simulate. You'll have X's in viz, diagram, waveform. But, you know, again, you should always be monitoring the log for messages. I feel like there was one other thing. Don't remember. Okay, let's start up again. So a little bit more combinational logic. We're going to find that by the end of this course, we've pretty much constructed a CPU out of muxes. Muxes are very fundamental and appear everywhere in digital logic. I'm assuming that you're all comfortable with muxes. So just quickly, the simple case of a mux, 2 inputs, 1 select line, 1 output. We can use a ternary expression to express that mux. The syntax of a ternary expression in Verilog, also C, JavaScript, Java, many other languages use the same syntax. So the select, the true case, and the false case, right? So if select is asserted, the output will be assigned to in1. If it's not, the output's assigned to in0. All right, and you can implement a mux in logic gates this way. You can do larger muxes, okay? And in Verilog, there are no less than 6 reasonable ways to code a mux. TL-Verilog favors, if you're doing one thing, you do it one way. In TL-Verilog, I tend to prefer the ternary expression for expressing muxes. None of those 6 ways is ideal for every scenario, but in general, ternary expression works out best. We'll use that everywhere. The one downside of the ternary expression is it's a prioritized mux, which implies more logic in some cases than you need. But anyway, we're going to use that throughout. So basically, to express a mux that has more inputs, you can chain the ternary operator. So your output, you can first look at the highest priority select line. In this case, it's select 3. If select 3 is asserted, we will send in 3 to the output. Otherwise, we'll have another ternary expression. If select 2 is asserted, send that to the output, and so on. So select 3 ends up being the highest priority here. We create this chain. It looks rather ugly when you nest it like this. It's a lot easier to read if you line it up this way. So here we're taking advantage of the order of operations of the ternary expression to drop the parentheses, right? This top case is going to get the highest priority if there's no explicit parentheses. So we can take advantage of that and kind of line up this expression like this, where it's much easier to say, okay, I've got, these 3 select cases and a default case, and those are selecting from these 4 possible inputs, right? So we're going to use this formatting for our multiplexers everywhere throughout this course. It's a little confusing that we have a 4-input mux, but we only have 3 select lines, right? It's a prioritized mux. If it's not 3, it's not 2, it's not 1, there's only 1 left. That becomes our default. Every ternary expression has an if and an else case. So just like the 2-input case, we only have 1 select. For the 4-input case, we only have 3 selects and a default. Okay. This logic expression, corresponds to this diagram, which is the same as this, except that prioritization is not clear in this picture. Okay. All good? This on the right? This one? No, they're equivalent. This is just easier to read is all. So just a little quick exercise with muxes. Go ahead and code the simple case, and then modify that simple case. You can also, we were just looking at multiplexers with multiple inputs. Also, your inputs can be wider, so you can operate on vectors. So go ahead and update that mux after you code this one to have inputs and outputs that are bytes. And this comment here, let me maybe jump out of here and explain that. So the point in that last statement is if I go back to an adder, for example, so I do an 8-bit adder is equal to 1 plus 2. I've put bit ranges on these to be explicit about the inputs. If I had a complete circuit here, there'd be an assignment of op1. That assignment would declare its bit range equals something. Once I have that assignment, I don't need the bit range here. We're taking advantage of TL-Verilog, just sort of assigning random inputs and allowing us to have things dangle. When you have inputs that are dangling, there's no assignment to declare their type. They just end up defaulting to a single bit. So if you're allowing the input to dangle, but you don't want it to be a single bit, you can force it to be a vector by being explicit about the range where it's used. Okay, and we're doing that here. So for this multiplexer example, right, you'll have to be explicit about the bit ranges because we're just letting those dangle. Tell it how wide they are. Make sense? How are we doing? I think you're mostly done. 30 more seconds or so. So just one more quick exercise with muxes. Let's take the mux that you currently have and widen the input. So currently you have 2 inputs. Let's stretch that out to 4 inputs. I'm just going to have this slide up, but you might want to refer to your copy of the slides for the chained ternary expression syntax. Yeah, and here we have 4 independent select lines packed into this vector. So you can reference one of those bits with the square brackets, right, like this, select 0. So use select 0 to select this first case in 0. So if you're having trouble, I walked through it myself. Solutions here. I noticed my priorities were backwards from what's in the slide. Otherwise, that should be correct. Okay, so if you don't have it yet, admit to defeat. We'll continue on. Everyone's good with this, I think. So in hexadecimal, of course, we have a long bit pattern. You can break it up 4 bits at a time. Each 4-bit corresponds to one hexadecimal digit. So we're getting into just some more Verilog syntax. And of course, TL-Verilog is inheriting this syntax from Verilog. So expressing constant values in Verilog, it's not just a value, it's a value in hardware, so it's got a discrete number of bits to implement that value. So this syntax is a 12-bit hexadecimal F0. So the base here, hexadecimal, is the base that's used to express the value here. So a couple more examples. We have a 16-bit value expressed as a decimal 5, a 5-bit binary 00111. You can use, you can omit the bit width if you're using 32-bit values. Sorry, that's not what this means. So a special syntax for tick 0, tick 1, which will give you a field of zeros or a field of ones. And you can omit everything if your value is a 32-bit value. So that is needed for this next one, which I know we're obsessing about muxes, but like I said, this whole course is muxes. So get this syntax ingrained in your heads. So starting from what you have, let's transition this from being what would be referred to as a one-hot select, where you've got an independent bit for every case, to an encoded select, where the select, surprisingly, is encoded. So we've got 4 different cases here. We need 2 bits to express the 4 different cases. The select then for case 0 in 0 is that the encoded select has a value 00, right? So the condition for the ternary that's selecting in 0 becomes encoded select is equal to a 2-bit binary 00. And then likewise for the others. Okay, so try to transition your mux from one-hot to encoded select. Okay, so we're transitioning from having 4 independent selects, right, where each bit corresponds to a given input, to an encoded select, where where we're specifying an encoded value of the input to select, right? So if the encoded select is encoding a value 0, we want input 0. If it's encoding a value of 2, we want input 2. Right? So in our ternary expression, we have all these select cases, right? And those select cases are going to be that the encoded select bits are equal to a particular pattern, 0, 0 for input 0, etc. Does that make sense now? we're mostly done here. Yeah. Interesting. So there's a TLV spec. This is basically a spec of the syntax, not the meaning, but use syntax reference. Mainly the best way to learn the language is to do courses like this and tutorials, right? So there's a bunch of tutorials. Each tutorial is one more concept in TL-Verilog. So we're going to do, this is the platform, combinational, sequential, pipeline. We're playing around with combinational logic. We're going to progress through these things as well. And then, so basically in this course, we'll get through validity, alignment, and then hierarchy state, and the remaining ones we don't even need for the CPU core. So if you want, after this class, if you want to continue on and learn more concepts, you can use these tutorials. It's a new language, new ecosystem. You can't ask ChatGPT to help you with your TL-Verilog logic. It doesn't doesn't understand TL-Verilog. You can't Google for answers. That's the trade-off, right? It's a better language, easier, more approachable language, but there's a lot more information out there about Verilog. So it's evolving, but this is what's available right now is mainly accessible here under the Learn menu. Some more Verilog syntax. So concatenation and replication of bit vectors. So if you need to form some vector of bits by collecting up other bits, you can use concatenation. It's the squiggly brace. And then expressions that you want to concatenate together. Replication. There are many choices that Verilog made that I think were questionable. This is definitely high on my list. Syntax for replication, open squiggle brace, the number of replicas, open another squiggle brace, and close them both. So this quantity, bits 4 down to 2 out of this vector foo, are going to get replicated 4 times and packed into a single vector. Now often when you're packing bits together, you're using a combination of concatenation and replication, which gets really ugly with all these squiggly braces. For example, right, concatenating foo with this 5 bits of 1. So just as a little bit of fun with this syntax, when you sign extend a signed number, you take the upper bit of that signed number and replicate it. So let's look at sign extending an 8-bit value into a 16-bit value, right? So you're going to take that upper bit of the byte and replicate that bit in the upper bits of the 16-bit number. That will give you a 16-bit representation of the same 8-bit signed number. So a combination of concatenation and replication here. Okay, so that's your task, is to finish this expression here for signed word that's 16 bits. to be an extension of the bit 7, 8 copies of bits. A lot of the issues I've seen with folks are folks who are familiar with Verilog, who want to code Verilog. Just code TL-Verilog. We can get back to Verilog later. But I think you're going to enjoy not coding Verilog once you get comfortable with not coding Verilog. All right. So actually, maybe I should comment on Srinivas, what you were asking earlier. So basically, the structure of a TL-Verilog file, right? I may as well walk over some of that, especially since a lot of you are trying to code Verilog syntax in the wrong context. So what's in this file? Basically, every TL-Verilog file starts with a line that identifies the language syntax. So this is a TL-Verilog file that uses syntax 1D. It has a reference to documentation, and this part says I want to enable the macro preprocessor, which is called M5. This says I want to express some macro preprocessing code. In this case, it's all commented. There's nothing here, but this would include the M5 standard library. And then I have a system Verilog region of code. This region will get completely ignored by Sandpiper. This code will just pass through. It's not ignored by the macro preprocessor. This is actually a macro, text macro, which gets expanded to this. So this is this module interface is what's expected by the MakerChip platform. This interface allows MakerChip to communicate with your simulation and your simulation to communicate with MakerChip. So MakerChip is providing a clock and a reset through this interface. It's also, for convenience, providing a cycle count, and your code is communicating back with the MakerChip platform to say when the simulation has completed, either passed or failed. So you've got these two passed and failed signals that you can assert. If you never assert them, you'll hit some max cycle count, which I think is set to 600. The simulation will stop. So the general structure of a TL-Verilog file is that your module declarations are just Verilog syntax. Those would be in an SV region like this, or looking at the macro expanded version like this. Inside the module, you can have TL-Verilog regions. So we get ourselves a TL-Verilog region, which enables the TL-Verilog syntax, right? By structuring it this way, we can have regions that we're guaranteed Sandpiper is going to ignore. They're just Verilog. This is especially useful as the technology evolves, right? If there is a bug in the TL-Verilog parsing, you know it's not going to, it shouldn't happen in this region. So you have kind of a safety net that there is a tool issue of some sort. You can always revert to Verilog safely. But in this region, the parsing applies for TL-Verilog. It's looking for expression syntaxes like, expressions like this that start with a pipe signal. This would be a reference to a system Verilog signal from TL-Verilog context. You just put a star in front of the name of the signal. It's actually optional. Having the star there just exposes it to the TL-Verilog parsing, which At current time, it's pretty meaningless other than the fact that it will actually show up in the diagram. The logic diagram here is a representation of the TL-Verilog logic. This is not going to represent any of your Verilog logic. And then to end the module, we go back into a system Verilog region and say, don't parse this. It's just system Verilog, pass it through. So some of the things that you folks were trying to do in Verilog, you can just code Verilog in the SV region. There are ways to intermix Verilog syntax here, but again, I'm focusing on TL-Verilog expressions, and we're just going to stick with that. Maybe sometime at the end, if we have time, we can talk about integrating with Verilog, but not the focus of the course. So jumping back to the slides. Yeah, okay. All right, so these labs are leading up to building a calculator circuit. We're going to start with the adder as part of our calculator. So code up this adder. You've coded similar expressions before. This should be quick. Check the waveform, make sure it's actually adding. After we do that, you're going to notice that the waveforms, it's hard to tell sometimes if the addition is right because we're adding numbers, they can overflow. Overflow in binary, if you add two values that extend off the range of the output value, it's going to loop back around, right? So this is basically a cyclic space in binary. If you extend out of the region, you're extending into the wrapped space of that region. So just for running simulations and being just able to see that it's doing an add, what you can do is limit the range of the two inputs. So in a sense, this is a mini test bench. And you can do that just by assigning the val1 input to a 5-bit expression and we have with checking on here. So you have to explicitly pad that with zeros, right? So this expression, val1 as a byte, is equal to 3 bits of 0 and some random, right? So now this is a dangling input signal, and it's just going to get the random value. So basically, we've just forced the upper 3 bits here to 0. And then you can do the same thing for val2, force the upper 5 bits to 0. Once you've done that, assign val1 and val2, you can drop the bit ranges on these inputs in the add expression. Okay, any questions on the lab? Number 3. Yeah, so the point here is just that if you're providing two random byte values, very likely they're going to overflow and not be able to be expressed in the byte output, right? So using 3 bits instead of 8, right? If you try to add 111 and 111, you're adding this value to another, well, let's just say 1. Let's say add 111 to a value of 001, right? That's going to take you off the end of the range that you can express in 7 bits. That's going to wrap back around, so 111 plus 1 is 0. Can be kind of confusing. So this is just to limit the range of our input values so that we're not overflowing. So, right, and the mechanism for doing that is to, val1 is a byte. We want the upper 3 bits to be forced to 0. The lower bits can be random. Just make up a name for a signal. That's a dangling input. It's going to be randomized. That makes sense now? Okay. Start with just step 1. It's just an adder. We've done that before. So this lab is sometimes more complex to explain than just to do it. So if you're confused by the lab, you can just type it along with me. So our sum is a byte. It's val1 as a byte. Plus val2 as a byte. So that's step one. Check the waveforms. I trust it's right. To avoid overflow, assign val1 as a byte. Retick E0. And similarly for val2, Okay, so everybody's got their adder? All right, so now we're going to look at a calculator. Okay, we've got our adder. Let's make a calculator that can do add, subtract, multiply, divide. All right, so in addition to your adder, make similar, you know, subtractor, multiplier, divider, just using these symbols. And hook them up to the same inputs, right? Our calculator just has 2 input values, and then it's going to perform all calculations at this point. Okay, so we're just building this circuit. Make sense? Probably one more for today before we wrap up. All right, so for this one, I have my inputs as before. I just added the 3 expressions corresponding to the 3 boxes here. Same as add, just subtract, multiply, divide. Um, so a calculator, of course, is only going to do one operation at a time, or at least it's only going to record one operation at a time. So we're going to select from among the 4 calculations the one that the one being requested. So we'll take in the 2-bit operation. We use a 0 encoding for sum, 1 value for diff, 2 for prod, 3 for push. So you'll notice in the circuit that we've designed, we're doing all computations in parallel. Okay? The nature of hardware is it runs in parallel. We can do things like this and just do all computations. The logic is there, whether you use it or not. So we just let the computation happen and select the one we care about. This might burn more power than necessary, so you might use some techniques to block off the computations that you're not using, but we're just going to go ahead and do the computation, select one we want. So add this mux here. Again, it's an encoded select, so we're comparing the op to a particular 2-bit value for each case. And yep, so you should be saving your files locally. finish, of course, you can stick around longer. You're welcome. I went through the solution myself, right? So the output is selected by the 2 bits of operand operation, either sum, diff, prod, or quote, depending on the value of the 2 bits of op. So to wrap up for today, just to kind of review what we covered, right? We covered combinational logic. So just stepping back to the beginning of today, right? We talked about the nature of digital logic, did some combinational logic examples, played around in NAND game. We talked about the chip ignite and tiny tape out. Difference of ASICs and FPGAs, what's inside an FPGA and ASIC, the carrier boards that you guys have been working, or the FPGA demo boards you guys have been working with. We played around in WalkWe and compiled our bit streams from the RTL that was generated out of the diagram in WalkWe and downloaded that onto your demo boards and saw it in action. We played around in MakerChip, got familiar with the platform, and then did a lot of combinational logic examples, right? So that was today. So tomorrow we'll go into sequential logic, pipeline logic. We'll start into RISC-V, compiling programs, assembling programs, looking at the instruction set architecture definition. And we'll look also a little bit at CPU hardware before you design your own, and kind of explore that whole stack of high-level software, compilation, execution on real hardware. So I think that's mainly in store tomorrow. Right. So again, we'll mill around for a while if anybody has lingering doubts or issues or questions. The boards you can leave on your desks. I guess we do have a new room for tomorrow because there's a little bit of static here. But we'll take care of your boards and migrate over. Do you need to say anything about the room tomorrow? It's all line of sight outside, so. Okay, so I'll see you all tomorrow. And can somebody confirm that the slides are accessible? Yeah. Okay. So the slides are linked from the GitHub repository, so just make sure you capture the GitHub repository as a bookmark or whatever.